Ladies and gentlemen, it's my great pleasure to welcome you to the lecture given by Dr. Erich Wimmer, lecturer at the Silesian University of Technology. Let me introduce our guest and invite, please sit down. It will take only a few minutes. Especially welcome our distinguished guest, Dr. Erich Wimmer. Erich Wimmer is co-founder and chief scientist officer of Materials Design, a company that develops software and provides services for materials research. At Materials Design, he is leading a team having so far over 100 major research projects for industrial customers. Dr. Wimmer is the author and co-author of more than 130 scientific publications and book contributions. He has given numerous invited talks worldwide, has been selected as an outstanding referee by the American Physical Society. He is also a member of the Materials Research Society, the American Chemical Society, and the American Nuclear Society. Congratulations. I also welcome Dr. Brian Drone, Commercial Director and in Sales and Support. Mikiko Ikeda, Computing Subject Matter Expert, Fujitsu Technology Strategy Unit. Professor Marek Niezgódka, Director of the Center for Computational Technology and Science, and the next Rector of the Silesian University of Technology, Professor Marek Pawełczyk. Marku is going to start his cadency the 1st of September 2024. Let me invite Professor Krzysztof Parliński from the Institute of Nuclear Physics. And I also welcome guests in the academic community of the Silesian University of Technology present at the seminar. Materials Design is one of the world leaders in application software for large-scale modeling of design materials for virtually and industrial sectors. The visit of Materials Design representatives is related to the continuation of the idea of the Center for Technology and Computational Science established at the University of Technology and the development of a program for the joint development of new application solutions in the field of computational design of advanced functional materials and their experimental validation. The priorities of the planned activities are closely linked to the main objectives of Silesia's transformation strategy, the development of environmentally natural and competitive industry, the improvement of the quality of life of its inhabitants, and the transformation of Silesia into a smart metropolis. I invite you to listen to the lectures. Professor Dr. Erich Wimmer, please take the floor.
Well, thank you for this very nice words of introduction, and thank you for coming to this lecture here. I have to say that this is my first time here in this part of Poland. Also, my Polish connection go back many, many years, especially with our dear friend, Professor Krzysztof Parliński. So let me just go right into the topic here about multi-scale materials modeling in the age of machine learning. Now, this morning I had a chance to see some of the facilities, and I was very, very impressed. Not only by the quality of the instruments and so forth, but especially by the competence and attitude of the staff. So I think that this university is in a wonderful position to be a leader and kind of a clear sign of success in the field of material science. And there, as you will see in this lecture here, there are plenty of opportunities. And this is also a golden time to combine leading experiments with leading simulations. So let me get right into it and talk about first our opportunities. And I always like to talk more about opportunities than problems or challenges. Because if you focus on problems, what you get is more problems. But let's focus on opportunities, because if you focus on opportunities, you get even more opportunities. Then I want to say a few words about the visionaries. When I look at what we are doing here in materials modeling, we are standing truly on the shoulders of giants. And I want to acknowledge at least some of them. And the next part will be very practical applications. We've worked in the last 6-7 years a lot with the American Electric Power Research Institute, especially on the safety and advances in nuclear power plants. So I will show some examples, especially from that field, but also touch on mechanics. And I do understand that in this university, you have fantastic capabilities in mechanics, with some applications, including, for example, shielding, that has a lot to do with understanding the interplay between a macroscopic strain and the atomistic behavior and response of the system. Also in catalysis and energy materials in general. So again, lots of opportunities. I have picked a few examples to illustrate our capabilities. And then I'll summarize and keep an eye on the clock here, because there's so much to talk about, and we want to have some time also for some discussions. So what are the opportunities, at least some opportunities that are listed here? Structural materials for engineering. So that includes alloys, advanced alloys, and it includes composite materials with nanostructures, and in particular I called out materials for shielding. Energy conversion. I think Poland has made a very, very smart move to recognize there's no way around nuclear power as primary energy. And we've seen in Germany last year the disaster of what happens if you shut down the world's best and safest nuclear power plants. Well, let's not comment on that, but what I can see happening is that very soon Poland will export electricity from safe nuclear power plants to Germany. And Poland has really deserved that. So, but also we're talking about e-mobility. Well, it's a nice idea to have primary energy from nuclear renewables and sustainable sources, and then use that for transportation. There is a long way to go, especially when you talk about transportation and like trucks and heavy equipment. Before we get a replacement of fossil fuels for these kind of applications, lots and lots of challenges ahead of us. And I do understand that this region here does have a tradition in chemistry. Well, I'm a chemist by training, and so that's wonderful to see that catalysis, there are lots of beautiful activities, and this morning I had a chance to meet some of the students and working in catalysis. So that's another area where modeling can and will play an increasingly important role. And last but not least, healthcare. Again, wonderful opportunities, and when it comes down to it, understanding materials, how to behave in a biological environment is very, very important. So, but what, when you talk with industry, what do they want? They want high performance. They want it to be durable, environmentally responsible. So, for example, there's a lot of activity in biosourced and biodegradable materials. Think about all the plastics and all the issues that we have with the pollution of our oceans. Yeah? We should be using available raw materials. It shouldn't cost much energy to produce them. I mentioned recyclable and biodegradable. When you really talk with industry, what they really want is not necessarily new materials, but they want their existing material to tweak that to respond to a new need. So it's the optimization of materials that plays a key role. Now, from a modeling point of view, what are the timescales? Well, it's years. Well, for example, an airplane lifetime is 20, 25 years. You have other systems like nuclear power plants. Well, we're talking about a lifetime of like 80 years. Length scale. Well, of course, the engineering length scale is meters. But when it comes down to atoms, you're talking nanometers. On the energy scale, well, you're talking terawatt hours of energy that need to be produced. But then in the catalyst, you worry about a few kilojoules. So what is actually for multi-scale modeling the biggest challenge? And I would argue it's actually the time scale. The time scale on the atomistic scale, for example, vibration of a hydrogen atom in water or in our bodies, that's femtoseconds, 10 to the minus 15 seconds. Here we're talking years. That's a tremendous challenge. And I will show you how we can tackle that challenge. But a few words about pioneers and visionaries. And of course, there are many, many. But I've picked up the three. John Clark Slater. He clearly had, already in the 1930s, a clear vision that you can use quantum mechanics, solve the Schrödinger equation in an approximate but useful way, such that you can treat and simulate real materials. And one of his students in 1937 calculated the energy band structure of copper, 1937. And he used a method that Slater suggested, was the augmented plane wave method, APW. Well, here we are in the year 2024, and our major program for electronic structure calculation of solids is VASP. And what does it use? Not APW, but PAW. In essence, the basic idea is still the same that Slater had. How do you describe electrons in a system? Well, near the atoms, they are kind of atomic-like. So in between, I don't know, I make a plane wave. So Slater clearly played a key role in moving this field towards real applications. Then I added another personality who is, of course, very well known here in Poland, Kołoś. What was his accomplishment? He was, I think, on a postdoc or on a scientific visit at the University of Chicago in the 1950s, and that was the time when computers became available. And he wrote a program to solve the Schrödinger equation for the hydrogen molecule with such an accuracy that he believed that, well, this is kind of a definitive answer with relativistic effect, with all kinds of effects included. But it disagreed with the then state-of-the-art measurements from Herzberg. Now, guess what happened? Herzberg redid the measurements, and then it agreed. So that brings me to a statement that Art Freeman, he was kind of my mentor and very good friend, said, never trust an experiment unless verified by a good, accurate calculation. Now, it's kind of a cartoon, but there's some truth in it. We can, in the calculations, if you do things properly and accurately, achieve incredible accuracy. And I will come back to this point at the end of my talk about the need for more accurate ab initio methods. We are all but at the end of the story here. So Kovács clearly was a pioneer and a visionary in this sense. And then there's Art Freeman. Art was born in 1930 in Lublin. And the family emigrated to the United States. Art then studied at MIT. He then became a director of the Francis Pitter Magnetic Lab, and then he accepted a position at Northwestern University. So yet another kind of Chicago connection. And he built up a team developing highly accurate ab initio methods. Art actually did his PhD with John Slater. He did calculation on an OH radical, I think. That was, in the 1950s, the state of the art. So, in a sense, I consider myself as a scientific grandchild of Slater, because Slater also worked with a friend and colleague of mine in Vienna, Karl-Heinz Schwarz. So there's a kind of a double connection with John Slater. And Art clearly had this vision that you can actually calculate properties of materials such that they are relevant for industry. Those are some remarks about the pioneers of the field. If we look today at what are the pillars, the foundations of what we're doing in computational material science, well, I think we can point out the three pillars. Of course, we take the fundamental theory, quantum mechanics, statistical mechanics, classical mechanics, electrodynamics as the solid foundation as given. But what are the three enabling pillars today are compute power, unprecedented compute power. Step back for a moment and think about what other technology that mankind has developed that has increased in performance and availability, in other words, cost, in such a way as computer technology. I mean, it was not all that long ago when John Bardeen, together with his colleagues at Bell Labs, developed the transistor. And I had actually a chance to meet John Bardeen in person way back in Chicago at a conference. And they were sitting next to each other for the conference dinner. And he said, yeah, I mean, we did have materials problems. And finally, we got the crystals clean and defect-free enough so that we can demonstrate the concept of the transistor. And then he said, actually, I didn't want to do that because my real interest was in superconductivity. He said, well, the management gave us the task to replace the vacuum tubes by something in solid state. So they did exactly the solid state realization of this concept of emitting electrons, having a gate and having a drain. They did it in solid state. But that was 1947, if I recall correctly, the invention of the transistor. And how did it change our world? Not just in computing, but also in communication. So we have compute power. And by the way, our friend from Japan would recognize this machine in Kobe, the Fugaku, right? So that's compute power. Then we have high throughput calculations. When you, again, step back, it was not all that long ago when we proudly did one electronic structure calculation, or maybe 3 or 4, and then that was a thesis. Today, we are doing electronic structure calculations for thousands of systems in an automated fashion, creating an enormous amount of data, consistent data. And that is really the basis for machine learning. Because machine learning and AI depends on the availability of large amounts of data. And that's a paradigm change. I mean, you're not doing modeling of a single system and try to find out the electronic structure and interpret it and write a paper, but you're generating enormous amounts of data. So these three components, three pillars, are what we have today to do materials modeling. Well, let's jump into some real examples. As I said earlier, it has to do with primary energy. Because in any kind of society, if you have access to affordable, safe, and sustainable energy, you have the basis of a healthy economy. If you don't have that, anything else, it will be very difficult. Now, nuclear energy has a kind of complicated history, I should say. Today we see a renaissance of nuclear energy. Quoting actually Mick Kai, who wrote this book, Renewable Energy Without the Hot Air, which you, by the way, can download for free on the internet. He said, well, if I look at all options to provide primary energy of renewables, he said, well, don't believe I'm pro-nuclear, I'm just pro-arithmetic. So safe nuclear energy has to play an important role. So what is the objective today? Well, increase the lifetime of the reactors, but also increase the residence time of a nuclear fuel bundle. Right now, it's of the order of 18 months, maybe 2 years. So imagine you can push that out and run it for, instead of 18 months, 24 months. Before you shut down the reactor, change the fuel, and restart it. And incidentally, when you look at some of the submarines driven with a nuclear power plant, I was amazed to learn how often do they refuel? Every 20 years. So you put in the fuel and then let it run for 20 years. And that's a small reactor. Well, there's no coincidence that there's large activities in so-called small modular reactors, SMR. So, for example, in the UK, Rolls-Royce produces the technology for the British nuclear submarines, and Rolls-Royce has formed a company, Rolls-Royce SMR, small nuclear reactors. And I understand that Poland is involved in SMRs. And they can be designed such that they are passively safe, and it's a wonderful technology. Now, just as a reminder, how does it work actually in such a nuclear reactor? Well, you have the core, which is under high pressure. Why do you need high pressure? Because you're cooling with water, and to keep water at like 360 degrees centigrade, you need high pressure. So that's the core reactor. And then water streams in, gets heated up in this core, and then there's a heat exchanger and a steam generator that drives the turbine, and you provide electricity. Now, typically when you look at the nuclear power plant, you say it produces like one reactor, 1.2 gigawatt electric. Well, but you have a loss of the thermal efficiency here. You're producing a lot of heat. And right now, heat is typically just released into the atmosphere by some cooling towers. But our friends south of here, like in the city of Brünn, they said, well, wait a minute. We've not too far away a nuclear reactor. Let's take the heat, make a pipeline, and heat the city of Brünn. And that's what they're doing right now. So we can use not just the electricity, but also the heat. And chemical companies like Dow Chemical in the US say, well, we need heat and electricity. So why don't we set up a small nuclear reactor, an SMR, on our site? And that's what's happening. So, but back now to the materials problems. Oops, sorry about that. So this core consists of these fuel bundles, and in the fuel bundles you have these cladding tubes. They are zirconium alloy, almost pure zirconium actually. And the fuel itself, you see here, that's uranium dioxide. They're these little pellets. They're stacked in these tubes. They're about 4 meters long. And you see here this gentleman assembling these tubes. And then you put it into this relatively harsh environment. So you have high radiation because high neutron flux that damages the material. You have heat and you have a corrosive environment, water. And one of the problems, of course, is that as you corrode the zirconium tubes, you form an oxide layer. But the process also generates hydrogen. Metal, Cr plus H2O gives you CrO2 plus hydrogen. And where does the hydrogen go? You don't want it to go into the metal because it forms hydrides with the zirconium and that embrittles, and you don't want this to happen. So there's a lot of effort understanding and modeling the corrosion process because that's at the heart of the long lifetime of the fuel bundle. So here we are again. You're talking about a time of the fuel bundle for maybe 18 months, maybe 2 years, maybe even longer. And on the atomistic scale, now we're down to the nanoseconds. So how do we connect that? Well, we need several layers. So let's set as our goal, we want to predict the microstructure evolution of the oxide film that is building up here. Because if we can reduce the oxidation rate, we reduce the production of hydrides, and we win all along. So what is the oxidation process and how does it, this microstructure, how does it come about? And that's actually a TM image from the group in Oxford of Chris Grosvenor. So now we need to somehow go from the atomistic world to this microstructure world. So what do we need? So we need time scales of days, months, and years. We need length scales of micrometers. So here's the scale. It's 1 micrometer. And in order to build up a physics-based model, you need the reaction rates, so the water reacting with the oxide formation. We need diffusion coefficients, thermodynamic properties as a function of stoichiometry. We need the phase diagram. We need elastic coefficients, so the tensor. We need interface energies. We need the fracture energies, electrical conductivity because it's an electrochemical process. Where do we get these properties from? We want to solve these equations. That's kind of the Allen-Cahn and Cahn-Hilliard equations that predict us the microstructure evolution. But you see, we need the free energy as a function of the chemical composition, the crystal structure, of the strain, of the interface energies. We need electrostatics. So we need a lot of properties. So how can we get them? Well, to some extent we can get them directly from ab initio calculations. So in the case of zirconium oxidation, you're forming the thermodynamic stable phase as the monoclinic CrO2 at a temperature of 1200 C. It transforms, it goes through a phase transition to tetragonal structure and eventually to a cubic structure before it kind of disintegrates or melts, if you want. Can we predict that? The answer is yes. And not only qualitatively, but quantitatively. That's a beautiful work done in the group of Professor Georg Kresse in Vienna. at the University of Vienna, and using a very elegant technology called machine learning on the fly, so force fields on the fly, or MLFF. So in other words, what he's doing is he's developed in VASP the capability. You start out with a molecular dynamics calculation on the ab initio level, and at the same time, you're training an interatomic potential. And as you go along, you use more and more this potential. Now, there's a technique that allows you to assess if this potential that you currently have is still applicable. If not, you go back, redo ab initio calculations, refit the potential, and do this dynamically. And at the end, you have carried out molecular dynamics simulation at the ab initio level, but at the speed of a force field. That's a very, very elegant method. And so if you exercise that, then let's just look at these numbers here. So that's the MLFF RPA, and predicted 1415, and experiment is 1400 for the phase transition temperature. And that's the tetragonal to monoclinic. That's this first phase transition. Now, what's very strange and scary is that, well, you start out with monoclinic and look at the volume. So the volume expands, and at the phase transition, it shrinks. So you get a volume change. Now, that has, and you do this again in the tetragonal to cubic transition. And we know that zirconium oxide are also being used in medical applications for ceramics. And there are cases where this phase transition from the stabilized high temperature phase transformed into monoclinic with a volume expansion. And that's a disaster. You crack the material. So even in medical application, you better understand very, very carefully your material's properties. But the bottom line is that here is a technology based on fully ab initio predicting quantitatively a phase transition. Now, that's not a small accomplishment. So, but we need many more properties. We need, for example, the stability of the tetragonal and monoclinic phase as a function of vacancies. Again, that can be computed. We need diffusion coefficients of oxygen, not just in the bulk various phases, but also in grain boundaries. So we need then models for describing multigranular structures. And now we are beyond the capabilities of direct ab initio, because you're dealing with like models of 10,000 atoms and you want to simulate long time scales. So there we have technology to create machine learned potentials based on systematic large scale ab initio calculations. And that's what's being used here. And that allows you to calculate all these properties. So we put it all together and see what we can do here. So now we are looking at a block of zirconium. We are initializing that with some initial oxide grains and supplying oxygen and putting in all these parameters that were computed and see what happens. So this is the metal part, this is the oxide part, and it grows. And that includes the mechanics, so the buildup of strain, the orientation, it has nucleation built in. And what do you see? You see that the interface is starting to get warped. So it's corrugated. You do get this columnar grain structure. And the size of this columnar structure is, well, you have a certain aspect ratio. And this is the analysis of the stress. And because you have a kind of a curvature, you have an interface that is not flat, you do get regions where, despite the fact that the entire system is under compressive stress, you get local regions that are under tensile stress. If you have a tensile stress, you can form cracks or nano slits and nanopores, and they have been seen in TM experiments. And if you have nanopores, those are pathways, highways, so to speak, of hydrogen to get in. So let's compare then this result from our simulations with experiment. Well, this is again this TM image. Look at the size, 1 micrometer, 1 micrometer. Well, I would say that's a remarkable agreement in the overall morphology. Also the fact that we're getting an interface that's warped. And this is after 40 days. That's not computing time, that's the time that we're simulating. So we have come from the nanoscale, from the atomistic level, all the way to the microstructure level. So a few words about machine-learned potentials. I mean, there's a lot of talk. I mean, it's a very, very hot topic. But at the end of the day, in a sense, is yet another force field with all the issues of force field, except the classical force fields. And here's one, the Buckingham potential that actually goes back to Born and Meyer, where you can, with a few parameters and a functional form that is inspired by the physics, describe a system like a lithium oxide. So you have 3 parameters. When you look at machine-learned potential of this zirconium oxide, you're using, in this case, 1,594 parameters. And that gives you the high accuracy, but also you're losing the direct physical interpretation. But it works, and these potentials reproduce remarkably well your training set and a validation set. So typically you plot then your values from potentials versus DFT values for the training and validation. Validation means that you're taking structures that are not explicitly in the training set and see how well it predicts that. And you see it's wonderful. Yeah. So how well does it work? I mean, here's another example of ceramic material, beta eucryptite. You probably never heard about, but probably you have already used it. Namely, in your cooktops, you have a glass ceramic. And when it heats up, you don't want any thermal expansion or stress. So you need a material that has basically no thermal expansion coefficient. How do you do that? You have a glass matrix, and you're putting in crystallites that have a negative thermal expansion. And beta eucryptite, that's this lithium aluminum silicate, has this property. And my colleague Jörg Hill, together with a colleague from industry, from Schott in Mainz, Wolfgang Mannstadt, created such a potential and tested it out. And yes, indeed, with especially this ACE potential, which is, by the way, developed in the group of Ralf Trautz in Bochum. We're collaborating with him. You see that we do get these subtleties of a thermal expansion with very, very remarkable accuracy. And actually, talking about machine-learned potentials, we've been invited last year to be guest editors of the Journal of Materials Research for a focus issue. And I encourage you to look at that if you're interested in an overview of MLPs. So we can make a check mark here and say that we've succeeded to go from ab initio quantum mechanics via machine-learned potentials to microstructure simulations, which you now can feed into your favorite finite element macroscopic code. Now, since this is a wonderful tool, can it also predict cracking? And in the oxidation, you have a so-called Pilling-Bedworth ratio. That means you take the metal, you oxidize it, and does the oxide actually take more volume than the original metal? And the ratio is the Pilling-Bedworth ratio. Quite often, as you oxidize, you expand the material, and you would have a positive Belling-Bedworth ratio. But there are also cases, and that's kind of surprising, magnesium. You oxidize magnesium, and magnesium oxide actually has a higher density, it shrinks. So can we simulate that? So here we have zirconium oxide, and we let it run, what you see is the formation of cracks, and there are lateral cracks. Well, I mean, you probably can make this experiment. You take a piece of cheese and squeeze it, eventually it will break in the other direction. That's exactly what we're seeing here. Now, what about magnesium? The Belling-Bedworth less than 1, and so you're shrinking. This is the oxide that forms, and now you're creating these vertical cracks because it shrinks. Well, that's not very good for the corrosion resistance of magnesium. So in other words, we now have tools to use parameters, materials properties that come from ab initio and force field simulations using these MLPs, putting them into this phase field modeling tool. So we can do other things. For example, we have a coating of a metal. So that could be metal B sitting on metal A, and then you apply a kind of a tensile strain. And what happens? You can basically simulate what the response of this coating is in response to the mechanical strain. That again uses a machine learned potentials, and then use it in our software with media and lamps, and you can do these simulations. You can also do, now that brings me back to this shielding. Well, how about if we take a particle and just let it impact on that surface? So we have a zirconium oxide particle, and we give it a momentum, what happens? Well, you see that the particle itself loses its crystal structure. On the surface, you're getting partial oxidation, and you're forming this interface here. And you also, what you've seen here, let me stop for a second, the initial shock wave. So you see this shock wave. So now we have a tool that not only allows us to study this kind of mechanical response on the atomistic level, but let's look closer actually from a chemistry point of view. Here we have zirconium as a metal. Here we have a zirconium as an oxide. And here we have zirconium that gets oxidized, because now you have zirconium atoms and oxygen atoms. That's wonderful. We have now a tool that allows us to describe chemical reactions with the convenience of force field simulations, but with the accuracy of the initial ab initio training set. That's a breakthrough. So let me just mention where we can apply this kind of technology, batteries. Well, what is the real problem with the batteries? Well, there are many problems. One of them is the energy density. If you compare isooctane, what is the energy per kilogram, and you do this with a battery, you find out that batteries, you need much more mass to store the same amount of energy. That means that your favorite car, electric car, is basically a huge heavy battery with wheels. That's a problem. But furthermore, we've seen more and more concern about accidents, because you have an electrolyte which contains organic compounds, If you damage the material, for example, in an accident, you get maybe oxidation and then a runaway kind of thermal event. And that's, of course, can be quite dangerous. So, what are the elements of a battery and what are the opportunities for improvement? Well, you have the anode. The best would be to have just the pure metal, pure lithium. But as we'll see, it creates dendrites. And if you make a dendrite and you create a short, then bad things will happen. So the lithium titanate, right now, the major batteries that, for example, have in your cell phone, that's graphite, lithium graphite. There are other solutions. Then the electrolyte, you have this lithium hexaperfluorophosphate as a salt. So lithium hexafluorophosphate ionized is your ionic carrier in the electrolyte. And also there's a variation, this lithium bis trifluoromethane sulfonyl imide, or lithium TFSI, which you probably have in your cell phone, with the electrolyte being in a fluid of ethylene carbide or dimethyl carbonate, ethylene carbonate and various other carbonates, and with additives. And of course, there's a lot of effort in solid state electrolytes. LGPS, so it's a sulfur-based compound, is a possible candidate. So there are lots of opportunities for optimization. And also on the cathode side, we've seen a trend from using not so much cobalt, which is for various reasons better to replace by, well, manganese is an option, nickel is an option, but also iron is an option, which is the lithium iron phosphate. So that's an interesting one. So, but you can imagine the chemistry of what's going on in charging and discharging is enormously complex. Just to give you an example of what properties we can compute is, for example, the density viscosity of the electrolyte. That's a mixture of this lithium hexafluorophosphate in EC and DMC. The experiment is the solid line. This is the calculation of the density. And here's the viscosity. Viscosity, you have two experimental curves, and those are the computed curves. Remarkably accurate. But I mentioned the problem with the lithium and the dendrite formation. So I asked my colleague Kyle, said, can you run with your phase field code the dendrite formation and apply an electric field, so an overpotential? If the overpotential is 0.3, let me play that. So this is the metal that forms, and this is the electrolyte. This is the interface. And really, not much happens, except at the very end, you see, you see a little bit of warping. But now, if you increase the overpotential, this is what happens. It starts out as a flat interface. It starts warping, and then all of a sudden, it's the electric field that overrides the density gradient, so that the chemical driving force, and you get this dendritic growth. So again, you're feeding in data from the ab initio and force field simulations, and you're doing this type of simulations. Now finally, and I'm realizing that I'm already using too much of your patience and your time, but a quick look at nanoparticles in catalysis. This is a cobalt nanoparticle, and in our company we have a PhD student, Marthe Bidot, She's doing fantastic work, has developed an interatomic potential, MLP, for cobalt that describes the bulk phases, HCP, FCC, BCC. It describes surfaces, nanoparticles of various shapes. And once you have such a potential, what you can do is, for example, take one of these nanoparticles and start heating it up. And that's what we're doing here. And what you see is that, well, it starts wiggling into more and more, and eventually it starts melting on the surface, and before it actually melts as an entire particle. And the melting temperature of a particle is much lower than that of a bulk cobalt. So you can then analyze this quantitatively, and she's using machine learning to analyze the molecular dynamics trajectories. So she's using a bispectrum descriptor to classify the various atoms. And then you can say, aha, here are the atoms on the 011 facet, and that melts here, and the other facet melts over there. Why is this important? It's important because we think about catalytic processes often. Here's a substrate, here's a nanoparticle, there are the reactants, that they go to the transition state, and you form the products. Well, in reality, these chemical reactions are highly dynamic processes. So it's the mobility of the particle itself, the catalyst, and the promoters, and all the players that act as a big concert. This quasi-static picture of a transition state is very useful, but it's a model. And now we can go much deeper looking at the dynamics of catalytic processes. So again, looking at the discussions we had this morning with the friends in catalysis, there's a wonderful opportunity to use these tools. Well, with that, let me start wrapping it up. I think it's fair to say that multi-scale modeling of materials is becoming a reality. I've shown you how you go from quantum mechanics via machine learning to interatomic potentials to materials properties in microstructure simulations. So ab initio quantum mechanics, they're wonderful in the sense that they are very generic. You don't need system-specific parameters. They have high predictive power. But in a sense, to be honest, these ab initio calculations that we use today, the Hamiltonians that we use, it's like using a GPS with a resolution of 5 kilometers. So it will get you beautifully from anywhere in the universe to Gliwicach, but it won't find the lecture hall. And so that brings us back to the work of Kovács. We need more accurate ab initio methods. And groups like Geocresse are diligently working on this extremely challenging problem. Classical interatomic potentials, they exist for metals, like the EM potentials, but they also extremely useful for organic systems, for polymers, and as such, I think they will remain. If you model systems where no chemical reactions take place, like structures of polymers, radius gyration, or solubilities or diffusivity of gas molecules in a polymer, or you want the TG, by all means use classical potential. They're extremely well tuned, and to some extent they can be more accurate than ab initio. So don't fall into this trap to say, well, I run ab initio, that must be the truth. No, you're making approximations. Interatomic potentials, classical potentials, tuned with experimental data, especially on the weak interactions, can be more accurate than ab initio. So, but of course, you're losing the ability to generalize it, apply it to any kind of system that you want, and describing chemical reactions. So machine learned the potentials that I've indicated do provide, I think, a major advance of the field of computational material science. It basically takes us to the length and time scales of classical force fields at the accuracy of ab initio levels. But we need large training sets. That means we need enough computing resources. And we can essentially reach the accuracy of the training set, but not more. They're not easy to calibrate afterwards. I mean, if you have 1,500 parameters, which one do you tune to get your melting point right? You don't have that. But so there's an opportunity for taking that further. Then I talked about this phase field-based approach to describe the microstructure evolution. And that's exciting because now we can combine the mechanics, the chemistry, even electric fields in an environment where all of a sudden you can go to phenomena in the range of days, months, years. So we have closed this enormous gap between the femtosecond of molecular and atomic vibrations to engineering scales. And then, of course, we have machine learning techniques and AI techniques to analyze these data and establish correlations. Again, we need to be careful. I mean, you have a lot of data, you establish correlations, but your correlations are only as good as the initial data. So you inherit these errors. So what is the truth? How do you validate what your machine learning tells you? So at the end of the day, it's always experiment. You need experiments tells you, yes, your theory, your approach, your model is correct, or no, you need to improve it. But it's clearly what we're seeing in machine learning techniques, neural network techniques from other fields like face recognition and many other applications of AI that we see today. It will have an impact on material science. But one of the big challenges clearly is for machine learning, you need large data sets. And quite often you just don't have that. So that means it's not a problem. It gives us lots of opportunities. So materials for advanced mechanical applications, lightweight, high-strength materials, for example, for shielding. Multi-component high-entropy alloys. So those are typical in alloy. You have a base metal like iron or nickel or titanium, and then you add elements to tune it. In high-entropy alloys, you have essentially almost equal amounts of different elements at different components, and that gives you new interesting properties. And the design space is just enormous. Energy conversion. We talked about materials for nuclear reactors. Well, there's a trend to investigate other materials than zirconium. For example, silicon carbide fibers embedded in amorphous silicon carbide. Then what we are seeing also in the field of nuclear energy, enormous and serious investments in fusion. And we've seen now that it's no longer kind of containing and managing the plasma. That's under control. What we need are materials for real reactors. The first wall, I mean, you would imagine in a fusion reactor that the energy is released to a large extent as very fast neutrons. Well, how do you convert 40 MeV neutrons into usable energy that runs a turbine that produces electricity? Enormous material challenges, but it's being worked on. Then catalysts. Well, I mentioned these nanoparticles, and we can take this further, put it on a substrate, and let it react. And that's, of course, a work in progress. Optical materials, magnetic materials, and materials for medical applications. And there are many more opportunities. So in other words, you've got your work cut out. There are plenty of opportunities. Just pick one that really interests you, and it's almost guaranteed you will learn something, you will contribute, and there's plenty to do for all of us. So let me wrap up with a few perspectives. We need higher accuracy in ab initio calculations. We're not at the end of the story here. And what Kowash showed us that, well, if you put your mind to it, you can get accuracy that challenges experiment. He did it for the H2 molecules in the 1950s. Now we need to do this for larger and complex systems. We'll have materials properties as input for microstructure simulations. Classical force field, as I mentioned, they will maintain their place, especially in modeling fluids, polymers, and the like. And machine-learned potentials may actually supersede the current reactive force fields because they inherit the reactive character of ab initio methods. And machine learning techniques, neural networks, will help us to manage and harvest all these data. So with that, I want to acknowledge my co-workers, but first of all, I want to acknowledge our customers of materials design. We are serving right now well over 700 organizations worldwide, many, many large companies, but also smaller companies, many universities, many national labs. So we have thousands of users, and they essentially help us to do what we're doing here. We have science sector technology partners. We have a close relationship with the group of Professor Georg Kresse in Vienna, with Anta El-Azab at Purdue University on the microstructure modeling. And then I have a space holder here. And I would like to see SUT here. And of course, I want to thank my colleagues at Materials Design, Michael Christensen, who did most of the zirconium work, René Windix, our battery expert, Marthe Bidot on the catalysis and cobalt nanoparticles, Volker Eyert on MLPs, Leonid Kaleb and Kyle Starkey on the microstructure modeling, and Clint Geller, who was a former customer who some 20 years ago said, we need to break out of the T=0 prison of DFT. We need phonons. So that's led to the collaboration with Krzysztof. And it was, well, going back to Clint Geller, actually. And now, well, he's retired from the lab and he's a consultant with us. So all of those I want to thank, and I want to thank you for listening to my talk. Hopefully it gave you some ideas and some inspiration. So thank you.
Thank you very much, Eric. And now we have some time left for possible inquiries, comments, and perhaps also suggestions concerning future activities. I should only mention one item, namely, you have got some, actually two references only to specific products of materials design during this lecture, but actually you get a whole portfolio of solutions for various scales of resolution in materials modeling. And from my personal perspective, I have to comment on it. It is the issue of merging quite different time scales if you want to reproduce phenomena that are driving the processes of material structure formation. You have got just one screen on phase field models, and I should share with you my personal experience. This means that you have to deal with parameters of more than 30 orders of magnitude different in a single model, and you have to cope with time scales ranging from femtoseconds to years in one simulation. And there is no way to escape from using simulation methods as the only existing approach. So, the floor is open. Krzysztof.
Yeah. I have written one page. Well, thank you. I would say therefore.
Yeah.
I want to better understand your name, machine learning. So, as I understand, you say the following. We take, for example, the ball of cobalt or the zirconium, and then we make a sort of a sphere or a ball, and then throw it to WASP and calculate the interaction. But that is too complex if you want to make it for a large ball. So you have to propose to WASP some approximation functions which will do the job in the best way.
Yeah. Well, the term machine learning, of course, there's a lot of hype associated with it, let's be clear. But what the idea is that you're right, you train, machine learning means that you are training some predictive algorithm on a large data set. And so in this case, these coefficients that come into play, they can be obtained with machine learning techniques, for example, a neural network technique. Yeah? So they're no longer fitted against like an empirical parameter, like an elastic coefficient or density, but you're training these machine learned potentials on thousands of configurations. So what to do is you say, I make a small subset, yeah, and for example, I deform that, I make a system with a vacancy, I make a surface, I subject it to some deformations, and you get energies, forces, and stress tensor. And then you take all of this information, those are kind of, and then you change it to a function. Either you train it, and the functions can be a neural network, so you have these kind of functions that are functions of a function of a function, or you train it against a descriptor that could be containing information about the local environment. So it's
number of the applied coefficients is less than.
Yes, that's right. So let's assume that you train on energies, on forces, on small systems. The forces give you maybe tens of thousands of data points, and then you're fitting against maybe a few thousand parameters, and you're using machine learning. That's the, yeah. And we can certainly.
Well, this discussion can last for hours, and I will give floor to Professor Parliński still, but I would like to give also an opportunity to other people. Well, you're welcome. What?
Thank you very much. Excellent presentation from Professor Wimmer. I do research in phase field method, so pretty you can be sure I will ask some questions about phase field method. So on slides 14 and 15, there you have made some presentations on the system like zirconium oxide zirconia and zirconium the interface modeling. there, my first question is, because whether it is, you have modeled it as a binary, like a zirconium and oxygen system, or just a phase, is my question. If you have done so, then whether, like in the binary system, how the composition in interface was defined. If the diffused interface composition like is not the same as the bulk phase interface, so in that sense, it may affect the accuracy of the simulation. So you have to make clear whether what was the theory used for the definition of composition at the interface, if it is defined as a binary, because you have clearly mentioned there is oxide, right? Zirconium oxide. Zirconium and oxygen are two elements there. And the second is in slide number 27, where you have modeled you have shown the slides of battery dendrite growth in battery using phase field method. And I see the paper by Hong and Vishwanathan was modeled using multi-physics object-oriented simulation environment MOOS software. So my question is whether your group materials design, whether a company also uses that software for that phase field simulation or not. These are the two questions. If you could answer me, I would be very grateful.
Thank you very much. Well, I'll do my way back as fast as possible.
Well, those are excellent questions, and in fact, at the heart of some of the phase field issues. Let me first address the question about how to treat the order parameter at interfaces, because and also we have simulations with multiple phases. So you have alpha zirconium, you have hexagonal CRO, you have monoclinic CRO2. You have tetragonal 02, and we didn't include the cubics. In other words, you have quite a number of phases, and in order to manage the multitude of phases and grain boundaries and avoid artificial coalescence, there's a phase, kind of a phase tracker that is implemented. For example, the diffusivity is different in the grain boundaries than in the bulk. And that was a very important parameter. So what we do is, in the phase field model, I mean, it's a finite element method, so you have a finite resolution, but you define an effective boundary, but you parameterize it such that it represents the real boundary that you describe with the atomistic simulations. That's how you deal with that. And then the second question, yes, the initial implementation is in the MOOS framework, because it's a very convenient framework, but there's an alternative like the MFEM from Zendia. So we are actually, in the test version, what you've seen here, this uses MOOS as the underlying differential equation solver. But we're also pursuing the MFEM implementation, which is more lightweight and actually faster computationally. Well, right now, the phase field model is not yet a product. Now we're working on a productization, and it's probably not going to be based on MOOS. Yeah. Yeah, but I mean, MOOS from the group in Washington, I mean, it's a very nice environment, but rather it's more designed for prototyping than for production. But very good questions. Thank you.
Well, okay.
Okay, thank you. That was a very interesting talk, and we had a little bit of this discussion in the morning. So I'm working on those materials that are called phase change materials, so they're melting at a certain point. And I saw that you predicted the melting point of zirconium or copper very, very well. And we're trying to do that with machine learning as well. And we're getting errors of 50 degrees. So basically, we're not able to predict this property correctly using machine learning and neural network as well. So do you see that there is a huge issue going from like just one metal components to larger organic structures when you're doing those machine learnings? Did you do a projects like that when you look into like organic molecules or salts?
Yes, we just submitted a paper actually together with a company that you may have heard of, British Petroleum, BP. And the question was, can we use machine learning potentials for organic liquids? The answer is yes, but it's tricky. And when you say machine learning, I mean, machine learning is a technique what ultimately you need to describe somehow the intermolecular interactions. So that means a force field. And we do have like 30, 40 years of experience in developing organic force fields. They can be very accurate. So the question at hand was, what about reactive systems where you don't have a force field? And what you realize is that the ab initio methods, especially for the weak interactions, are not good enough.
Well, we use polarizable force fields.
Sorry?
We use polarizable force fields?
Yeah, but you can use polarizable force field, you can use reactive force fields like REXFF, and you find out, especially for subtle quantities such as phase transition temperatures, they're not good enough. And it's not machine learning, it's the potential, it's the physics that you're not capturing properly. But, and I didn't have a chance to talk about this, in the work that Georg Kresse showed, you saw MLFF delta and RPA delta. What you can do is you can create a training set on a certain level of theory, like density functional PBE standard with all its errors and uncertainties. Then you take a subset of that and you perform high-level quantum chemical calculations. And you train the difference between the kind of lower level and the upgraded potential. And that delta can be expressed again as a machine learned potential. And then you take your large training set on the lower level, you upgrade it, and then you do the fitting. So that's a strategy to get the accuracy of high-level calculations, but the diversity from the initial training set. And it shows you how subtle nature really is. I mean, the getting a phase transition right, the temperature, it's just minute. And the Gibbs free energies, they cut it on a very, very shallow angle. So it's not a problem, it's an opportunity. There's lots that we should do and could do.
Thank you. I hate to say it, but we are really close to the time limit. So last question, if any. Well, so this gives us both an opportunity to make a kind of preliminary announcement, namely, all of these solutions and technology for materials design, simulation, modeling will soon become available at the Silesian University of Technology, at newly founded Center for Computational Technology and Science. That is a joint undertaking which will be signed in a form of agreement within the next 1 hour. And so please, in case you have any real interest in having use of these opportunities, so you are most welcome to contact the organizers of today's lecture and learn more about future possibilities of using this at the premises of the Silesian University and also at our partners, companies, organizations providing us access to the frontier computing technology. Thank you very, very much for your attendance, and thank you, Erich, for your fantastic lecture. Well, I hope it is just beginning, And one more announcement. Within a few months, we are planning to launch a joint workshop on these techniques, solutions, and also giving an opportunity to discuss the possible joint undertakings. Thank you very, very much.
Start here.